The objective of this video is to review the course trajectory and narrative of AC machine design. At this point, we're over 2/3 the way through our semester, and we've just finished up a unit on winding design and are about to launch into a bigger picture unit on the evaluation of AC machines and how you know if you have a good machine. So it makes sense at this point to take a step back and think about how all of our work fits together and how all of it builds towards designing an electric machine. And I want to do this by focusing you on the machine sizing expressions that we developed about a month ago. And those expressions are in terms of the torque of our motor, and we relate them to physical quantities of the motor. That is the volume of our rotor and the shear stress that our rotor experiences that causes it to rotate. And so each of these aspects, the volume of the rotor, the shear stress, can be broken up into key independent decisions in our design process. So let's zoom in on the shear stress, which we had written in terms of our magnetic loading. That's B delta hat. That was the peak value of our fundamental harmonic of magnetizing field in the air gap of our motor. And A hat, which was the peak value of our equivalent linear current density that is creating current linkage in the air gap of our motor. And so we spent quite a bit of time talking about both of these, and what I want to do here is highlight the design decisions and the units of the course that went into thinking about each of these components. So let's start with B delta. This is related to the design of the main flux or the magnetizing flux of our machine. And we determine what B delta is. We create B delta by placing permanent magnets on our rotor, or by having a wound field salient pole rotor, a field winding on our rotor, or through a squirrel cage. And we've talked about the first two of these quite a bit, but we haven't talked about squirrel cage rotors much yet. The second quantity here, A hat, is our electric loading. And we create electric loading through the design of our stator winding. And our key decision points here is the number of slots per pole per phase, and the number of turns within a coil, the number of layers in our winding, and the pitch of our coils. And so we've just spent quite a bit of time talking about how you determine all of these things in our winding design unit. And the sign phi is something that our motor drive determines. This is determined at runtime. It's not a design time decision. We talked about some rules of thumb for how you determine what the sign of phi should be based on the machine type. So for induction machines, this might be 0.8 because you have to provide some magnetizing current with your stator winding. And you can go back to our machine sizing unit to look at those considerations. What we haven't talked much about is the volume of our rotor. And this is related to the mechanical design of our motor. So there's two key decisions here. The volume of the rotor is pi r squared times L. So it's pi times our radius squared times L, just the volume of that cylinder. And the two decisions are what your radius can be or should be, and what your length of your rotor should be. And your radius is limited by the mechanical strength of your rotor design. So if you've got permanent magnets on your rotor, it's going to be limited by the speed at which those magnets will fly off. Or if you put a retaining sleeve on those magnets to hold them onto the rotor, it'll be limited by the strength of that retaining sleeve, how effective it's able to hold them on. If it's a squirrel cage rotor, you have similar considerations. At what point will your squirrel cage break apart? Or if it's a wound field rotor, at what point will your rotor fail? And what you can do as an electrical engineer to answer this without extensive analysis is that you can look at typical tip speeds or surface speeds of your rotor and make sure that you are within those surface speeds. And if you survey the high-speed machines literature, you'll find that typically this is going to be under 200 meters per second, but 200 meters per second is pretty hard to do. So much more practically, this is going to be under 150 meters per second. And in fact, anything with a surface speed over 100 meters per second is considered a high-speed machine. If it's below 100 meters per second, that's acknowledged to be a much safer design with less need of careful audit of your mechanical strength. And then the length of your rotor that's that second variable that we have. So we said we had the radius and the length that we had to decide for the volume of our rotor. The length of the rotor is limited by rotor dynamics. And we are not really going to get into that in this class. That is an extensive topic area of its own. But basically, when you have a long, narrow rotor, you start to get a standing wave appearing on your rotor at certain speeds, and that is a problem. It can lead to vibrations, it can lead to bending modes where your rotor actually becomes flexible, and this can cause failure in your motor system. So typically motors are designed so that they only operate below their first critical speed. And again, that's only a typical case. Of course, there are designs where rotors will go into the critical speeds and maybe even operate above flexible bending modes. But a crude rule of thumb is that you design your rotor to have a short enough shaft length so that you stay below your critical speeds for your entire operating range. Okay, so in summary here, we've got our torque sizing law, and we really like this law because we can view it as the summary of key design decisions that we make along the pathway of our motor. So we've got the volume of our rotor, which we can limit by the mechanical considerations of the machine design. That is the critical speeds and the mechanical strength of the rotor. And then we can talk about independent decisions as far as what our magnetic loading can and should be. And we've got rules of thumb for what reasonable values of magnetic loading are. And the electric loading, what that can and should be. And again, we've got tabulated values for what reasonable electric loadings are based on your cooling approach. So this allows us to get a quick first pass at our machine sizing and our machine dimensions. And it also brings together the key units of this course. So in this course, we're primarily talking about the design of the magnetizing flux and the design of the electric loading. And now we're transitioning away from analytic design of these topics to saying that you have a candidate machine design. Now, how do you determine whether it is a good design? So now I want to give an overview of the design process. And the first step in the design process is that we have to somehow create a candidate machine design. And what do I mean by that? Well, I mean we need to somehow determine what the geometry for the machine should be and what the dimensions of that geometry should be. So in homework 2, we gave you a parameterized cross-section of a permanent magnet motor. And you can see that that parameterized cross-section had a lot of variables linked to the various dimensions, the tooth thickness, the tooth tip thickness, the radius of the stator, and so on. And so your first task when you're going to design a motor is to come up with some kind of guess for what all those dimensions should be, and also to determine what your winding layout should be within the slots of that motor, and what your excitation should be. How much current is your machine going to be rated for? So you make a guess at all of this, or you make a design of it. You intentionally have design expressions that you evaluate to come up with these dimensions, but you don't know if it's right because you made a lot of simplifying assumptions along the way. Maybe you assumed linear materials, or you had neglected harmonics, but somehow you came up with a candidate machine design, and that candidate design had all of the dimensions, the winding layout, and the excitation attached to it. And then you need to figure out if that design is any good. And so the way you figure out if your design is any good is first you do the magnetic analysis of it. That is, you need to calculate your magnetic fields in the cross-section of your machine. And so you'll use either an FEA technique, like we've been doing FEM in class, or magnetic equivalent circuits, like we talked about in the beginning of the class, or you'll take a direct solution to the fields. But the point is that you are going to calculate the fields in the cross-section of your motor, and you're going to use that solution of the fields to determine your torque. So you'll feed those fields into the Maxwell stress tensor, and out will come the torque of the machine for any given rotor location. And you can use that to determine the torque density, how much torque ripple you have. You will also use those fields to determine the losses in your machine so that you can get an efficiency calculation. In addition to that, other criteria that you might use to determine if your design is good or not might be how much the machine will cost to build, what the active material cost is. If you've got a bunch of copper, a bunch of steel, how many dollars per pound of copper and steel is the current trading price, and if you know that information, you can figure out how much the raw material cost of your particular design is. What equivalent circuit parameters, what the power factor of the machine is, and I just wrote etc. So you can imagine you might have other things that you really care about. So it's whatever you care about, whatever the functionality that you decide matters for this motor is how you determine if this motor is going to be good enough or not. And so you evaluate these metrics and you decide if the machine design was good enough, then you're done, you're happy. If it's not good enough, then you go back and you refine your candidate design and you repeat this process, you try again. And the last thing I want to point out in this is that the way you create this candidate design might be done through analytic design steps, or it might be created for you automatically by an optimization algorithm, or some combination of both. So in summary, this video has given you an overview of the machine sizing process, and then use that to tie together all the units of the class so far. And that is the design of our main flux path and our winding design unit. And then we've given an overview of the machine design process, how we create a candidate design, we evaluate that design, and we decide whether the design is good enough. And this gets into the need to be able to calculate the magnetic fields in the cross-section of our machine, which ties together our class units on finite element analysis, magnetic equivalent circuits, and our simplified techniques to the direct solution of Maxwell's equations for fields.